So let's see how to get a chi-square test statistic calculated in Statkey, and then see what we can do with this test statistic once it's calculated. In Statkey, we are going to, under More Advanced Randomization Tests, you'll find chi-square goodness of fit. So this is where we're going in Statkey. Way down here at the bottom, More Advanced Randomization Tests, chi-square goodness of fit. We can see we have to enter our data at this point, and these are our data right now. We want to enter these commas, as you can see, between the label and the number, and we don't want to enter anything else. So I'll click on the Edit Data button. I'm going to delete everything here and start with blue, 26, brown, 11. It doesn't matter whether you put spaces or not. Green, 14, orange, 20, red, 8, and yellow, 11. But then, since I don't have any header row, I want to uncheck Data has header row. If I had left the labels of choice and count in there, then I could leave Data has header row selected. So just make sure that whatever you have checked down here matches whatever you've entered. We never use raw data for this particular test. So the only thing you have to pay attention to is the data has header row. That gets us our counts over here, we can see. And let's just click on null hypothesis and see what we've got in here by default. That same proportion that we calculated, 1/6 for each color, the default null hypothesis is that all of the proportions are the same. So we'll say, okay, that does look like the correct null hypothesis for us. Notice up here we have our chi-square test statistic, 15.202. That's the same thing that we got by doing our chi-square test statistic by hand. We also have our sample size of n equals 90, verifying that we entered our data correctly. So our null proportions are 0.16666, etc., right? And that is the equal proportions. So those look correct. Each one is equal to 1/6 within rounding error. And that 6 looks a little bit bad. Our chi-square test statistic we said was 15.202. And we're going to generate a randomization distribution this time. We're going to go to a theoretic distribution soon, but first let's just see the shape of this randomization distribution. So I'm going to come back and generate 1,000 samples. Maybe another 1,000 is fine, right? And we can see that this is a right-skewed distribution. Unlike a lot of the other inference that we have done, this doesn't look like a bell-shaped distribution. And in fact, it shouldn't. In general, it will not look like a bell-shaped distribution. We have a lot of right skew in this. So this is a right-skewed distribution. And we're going to now find our p-value by placing a check mark beside right tail. And in doing so, let's think about why is it the right tail and not two tails, right? If we think back to what we said when we first calculated our chi-square test statistic, the larger that statistic is, the further our observed values are from our expected values or our expected counts. So we do a right tail because we're really interested in the question of how big did that chi-square test statistic turn out to be. It's going to get bigger regardless of whether our observed counts are larger or smaller than our expected counts. They always make a positive contribution to the chi-square test statistic. It's always true that that test statistic gets larger if the null hypothesis is false. So this is always done as a right tail when we're doing a chi-square test. Now I still need to overwrite this 12.535 down here with my chi-square test statistic, which is 15.202. And I can see that I get a p-value of 0.0065. So, scrolling down a little bit, I now realize I want to move that answer down to here and answer the question that we just described verbally. The reason we're interested in a right tail is that a large chi-square test statistic is evidence against the null hypothesis. So we're going to write a two-part conclusion. Let's go ahead and keep this example open in a browser tab because we're going to want to look back at it again soon. But for our conclusion on a multiple comparison type of test, we have two parts. Part one is just based on the p-value. So based on this p-value of 0.0065, how strong is our evidence against the null hypothesis? Pretty strong, right? This is a very small p-value. It is smaller than 0.01, so we have very strong evidence that the number of each color of M&M that's put into the bags is on average different. Part two, where is this difference observed? For that, we have to look a little bit closer, and we have to look at each cell's contribution to the chi-square test statistic. So let's make our statement about part one first. We don't have to label these as part one and part two, but I'm going to just because we're learning this right now. Part one, we have very strong evidence that the proportion of each color of M&M is not the same. Or we could say that the proportions of each color of M&M are not all the same. We're not saying they're all different, remember. We really just mean that at least one pair is different from one another. Now for part two, we have to go back and look at each cell's contribution to the chi-square test statistic. For that, I am going to go back to Statkey, and right over here where it says original sample where we got our chi-square test statistic, I'm going to click on that show details button, and that brings up three values for each cell. The legend is down here at the bottom. Observed, expected, contribution to chi-square. So for blue, we had 26 blue M&Ms in our sample. The expected count was 15. Under the null hypothesis, we would expect to see 15 blue M&Ms in each sample. The contribution to the chi-square test statistic, which we calculated by hand, is 8.067. Now looking at all of these numbers in blue, I want to pick out the one that's biggest and make a statement about that for part two of my conclusion. So it looks like we see the biggest contribution coming from blue M&Ms. I have to say a little bit more than that. I saw 26, I expected 15, and therefore I want to say that we see more than expected of blue M&Ms. So the largest contribution is from blue M&Ms, in which we saw, or we observed, more than expected. We don't want to say how many, because that's a statement about our sample. And our conclusion is mostly about the population, right? So really we want to indicate which cell made the largest contribution, and in that cell we either observed more than expected or less than expected. We want to make it clear, or fewer than expected. We want to make it clear which of those is the case. So this is a two-part conclusion, and most of the time in a multiple comparison type test we're going to want a two-part conclusion.